Good morning, students. In last lecture we have studied one method to solve second order linear differential equation. It was the method when one integral of CF is known. Today we discuss normal form. Actually, normal form is that form of a differential equation in which first order derivative is absent. First order derivative is absent. So we are given with a differential equation, second order linear differential equation in the form d2y upon dx square, that is y double dash plus py dash plus qy is equals to r. Here p, q and r are some function of x. We are to convert this equation into normal form. Means in resultant equation first order derivative must be absent. To convert it into normal form, we use some transformation, and here we convert dependent variable y into some another dependent variable, and resultant form will be of this type: d2v upon dx square plus iv is equals to x, where I and s are some function of x or constant. So to convert it into normal form, we use a transformation y is equals to uv. Now differentiate y with respect to x, we get dy upon dx is equals to du upon dxv plus u dv upon dx. Further again, differentiate dy upon dx with respect to x, we get d2y upon dx square, and d2y upon dx square is given by this equation: v d2u upon dx square plus twice du upon dx dv upon dx plus u d2v upon dx square. Now putting the values of d2y upon dx square, dy upon dx and y, which is uv, in equation 1. Equation 1, y double dash plus py dash plus qy is equals to r. Here we put the value of dependent variable y and its derivative. We get this equation. This is value of d2y upon dx square plus p dy upon dx plus q y is equals to r. Now we rewrite this equation as a second order differential equation in variable v. Second order differential equation in variable v. So we have d2v upon dx square with some coefficient, then we have dv upon dx with some coefficient and v with some coefficient. So we get u d2v upon dx square plus pu plus twice du upon dx into dv upon dx plus d2u upon dx square plus p du upon dx plus qu into v equals to r. Now divide this equation with coefficient u. We get equation number 2. Now in this equation 2 we are to remove first order derivative. So what we do here, we take p plus 2 upon u du upon dx is equals to 0. That is, coefficient of dv upon dx must be 0. In that case only first order derivative will be absent. So coefficient of dv upon dx equals to 0. We get du upon u is equals to minus half p dx, or we can say du upon dx is equals to minus half pu. Now integrate this equation both sides. In left hand side we get log of u, and in right hand side we get minus half integration of p dx. So we get value of u is given by u is equals to exponential minus half integration p dx. Now replace this u in y is equals to uv. we have y is equals to uv. Now putting the value of u in y, we get y is equals to exponential minus half p dx into v. Now differentiate u with respect to x. We have already from here du upon dx is equals to minus half pu. So use this du upon dx is equals to minus half pu. Again differentiate it with respect to x, we get d2u upon dx square, which is equals to minus half p du upon dx minus half u dp upon dx. And now replace d2u upon dx square du upon dx in this equation. So equation 2 become d2v upon dx square. Here first order derivative dv upon dx is absent, as we already take p plus 2 upon u du upon dx is equals to 0. And in third term, which is coefficient of v, replace d2u upon dx square and du upon dx. We get this equation. Now simplify this. We get d2v upon dx square plus q minus 1 by 4 p square minus half dp upon dx into v is equals to r upon u. Or we can rewrite it as d2v upon dx square plus iv is equals to s, where I is represented by q minus 1 by 4 p square minus half dp upon dx, whereas s is given by r by u. Now here it's I, this I must be a constant or a constant upon x square form. If I is constant, then this equation become a linear differential equation with constant coefficient, which can be solved. Or if I is constant upon x square, I is constant upon x square, we can convert this equation in a homogeneous equation. Homogeneous equation means index of x must be equals to order of derivative in each term. So if I is constant upon x square, we will multiply this equation with x square. So here we get x square d2v upon dx square plus constant into v is equals to some function of x, which is a homogeneous equation. So in both cases we can solve. But if I is other than constant, I is other than constant or other than constant upon x square, we cannot solve this equation, and whole process whatever we done is meaningless. Now we try to solve a problem. Here we have an example, d square plus 2xd plus x square plus 1y is equals to x cube plus 3x. Here this equation is already in standard form. Coefficient of d2y upon dx square is 1. To solve this problem as a normal form, first we convert y into uv, where u is given by exponential minus half p dx. Here p is what? Coefficient of dy upon dx, which is 2x. So exponential minus half 2x dx, we get u is equals to exponential minus x square by 2. Now we are to check I. If I is constant or constant upon x square, we will calculate v. Otherwise it is of no use to use this method here. So calculate I is q minus 1 by 4 p square minus half dp upon dx, and here q is coefficient of y, which is x square plus 1. Coefficient of y, x square plus 1. So calculate I, and we get I is equals to 0, a constant. So we can apply this method. So equation 1, which is d2v upon dx square plus y is equals to x. it becomes d2v upon dx square is equals to r upon u, or d2v upon dx square is equals to x cube plus 3x upon exponential minus x square by 2. Now we will solve this equation. To solve this equation, first we take dv upon dx as q, so it becomes dq upon dx. Taking dv upon dx as q, we get dq upon dx is equals to x cube plus 3x exponential x square by 2. Now integrate this equation both side with the integrate this equation both side. We get q is equals to integration of x square plus 3 exponential x square by 2 dx plus c1. Now to solve this integration, we will solve this integration by substitution method, taking x square is equals to t. When we replace x square with t, we get here t, and this x dx become dt. So we get q in this form, and we will integrate this term by parts. This t plus 3 is first function u, this exponential t by 2 is second function v, and we will integrate this by parts, and we get q is equals to t exponential t by 2 plus exponential t by 2 plus c1. Now as we assume q is dv upon dx, so we get dv upon dx is equals to t exponential t by 2 plus c1 plus exponential t by 2. Now we can rewrite this as dv is equals to this term into dx, and integrate both sides. We get v is equals to exponential x square by 2 dx plus exponential x square by 2 dx plus c1x plus c2. Now first we integrate x square exponential x square by 2. To integrate this, we separate this term like x into x exponential x square by 2. This is what x square, separate x square, x into x, and taking first term as x and second term as x exponential x square by 2. And now we will integrate this as by parts, with by parts as u into v form. And using this formula, this integration convert into x exponential x square by 2 minus integration exponential x square by 2. This second term, when we put this integrand into v, the second term will be cancel out with here second term. So this v becomes v is equals to x exponential x square by 2 plus c1x plus c2. So we get y is equals to uv is complete solution, which is given by y is equals to x plus c1x exponential x minus x square by 2 plus c2 exponential minus x square by 2. So that's all about normal form.